Okay, welcome to this Henstitute. I'm going to help out with electrostatics problem number 33. We've got these 4-point charges. They all have the same magnitude, so we know what Q is. Q is this value right here. And they're at the corners of a square that's 4 centimeters on a side. That's going to be important. So let's just go ahead and draw this out. So we've got a charge here, a charge here, a charge here, and a charge here. So these are the corners of a square. No, that's not the best square, and this is 4 centimeters on a side. So 4 centimeters by 4 centimeters. And it says 3 of them are positive and 1 is negative. It doesn't really matter how we do it, so I'm just going to go positive, 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 negative. Now what we're looking for is the net electric field at the center of the square. So the main equation we're using, the electric field produced by a point charge is K, our 8.99 times 10 to the 9th. For K times the charge, I'm going to write that as big Q, divided by R squared, where R is how far away from the charge you are. So as I do this particular problem, I'm looking for the very center of this particular square. So the R is going to be how far it is from a corner to that center. So the first thing I'm actually going to find is, let's figure out how do I find R. Now, if I do this problem, there's a couple of different ways to go about it. One method that I usually think of is, I realize this is 4 centimeters, that this is a big right triangle, and so this entire distance from one corner to the other corner can be found because it's the hypotenuse of it. In other words, if I want to find that hypotenuse, c squared equals a squared plus b squared, where these two are the same. So this is 4 squared plus 4 squared, and then that's c squared, where c is the entire distance across. So this can be 16 plus 16, or 32. So it's going to be the square root of 32 for c. And then remember that r is going to be half of that. So r would be the square root of 32 over 2. Now, thinking of that, I could actually plug this into a calculator and find that value. We could do it a couple of different ways. We know that 32, we can pull out 4, things like that. I'm going to go ahead and find a decimal equivalent. So I'm going to take the square root of 32, I'm going to divide it by 2, and I get that this value is about 2.828. And that's in centimeters. So keep that in mind, because we actually eventually want this in meters, but I've been doing everything in centimeters. So R here is actually going to be 0.02828 meters. So that's the first part. The second part is a realization of what each one is doing. So electric field actually has a direction to it. It's a vector, and it's always the direction a positive test charge would move. So if I were to put a positive test charge here at the center, so it's a positive charge, what would each one do? So as I kind of go through here, this charge up here is going to repel it, so it's going to push it in that direction. If I look at another one of these charges, this charge up here is also going to repel it. This charge down here is also going to repel it. But this charge down here, I'm going to make this one blue so we can see it, this negative charge is actually going to attract it. So the size of all those is exactly the same, but if I look at these two, if I look at this group right here, they are pointed in opposite directions, so they're going to cancel each other. So I don't actually need to even worry about these two because they're canceling. The ones I have to worry about are these, and each one, the blue and the green one, are equivalent to my E. So really all I have to do is find E for one of them, and then the net electric field would actually be 2 times that E. So I'm just going to take my K times one of these charges, which is given up here, and then divide by my R squared down there that I have. So I plug in that number, I plug in this number, I plug in that number. That's going to find E, and then I just have to double it, and I now have the net electric field. So you have to kind of draw this out a little bit, as well as kind of use a little bit of geometry in this particular problem. I hope that helps.